So if you remember, we talked about the rate of reaction and then we talked about the factors that affect the rate of reaction. That means what makes a reaction faster. Now, is it important to make a reaction faster? Of course. If the reaction is too slow, I got everything at once. With what everything inside, I got scared for a while. Okay, if a reaction is too slow, especially for those reactions that take place in the factory, we need them to be faster. Okay, now certain reactions, we can get them to be, we want them to be slow. So, for example, the spoiling of food. Okay, the spoiling of food, we want it to be really, really slow. So therefore, food we keep in the fridge, we keep in the freezer. Okay, so this is common things that we use in everyday life. Okay, now, do you guys know what a sawmill is? Do you know what's a sawmill?
Saw milk?
Sawmill. Sawmil. Sawmill. Do you know what that is?
No idea.
Okay, so sawmill is where they cut wood every day. You get it? Okay, so sawmill is like this. Basically, they saw the wood lah. Mill is basically a word to say a factory. Okay, so okay, sawmill is like this. You know, all this wood, they want to drill it, cut it to the size that they want. So they have a saw that goes through it like that and it turns round and round. You know what I'm talking about? So because of this, do you think there's many tiny pieces of wood dust or sawdust everywhere? Yes, so that is called sawdust. The tiny particles of wood that are flying around in the wood factory basically is called sawdust. Okay, now in a flour mill, okay, so what happens is you're taking IG. So sometimes they will say things like flour mill, sawmill, and everyone is wondering what are they talking about? Those who are not those who don't know lah, okay, because we don't use these kind of words commonly in everyday language. So a flour mill is basically the same concept, except in the factory they're making flour. Okay, in a factory that they're making flour, do you think there'll be a lot of flour in the air? Okay, so a sawmill factory and a flour mill factory, as well as where they mine for coal, a coal mine. Okay, do you know what is coal? Coal is basically charcoal, like the one for barbecue. Okay, the coal mine and is also where I have tiny particles of coal dust. That means the barbecue, that coal, the dust. Okay, what do these three dusts have in common? They are basically carbon. They are basically carbohydrate. They are basically made from carbon. And if I have a piece of wood, it will burn. If I have a block of flour, it will burn. If I have a piece of coal, it will burn. Correct or not? If I take my wood and I cut it into smaller pieces, it will burn faster. That's why they use wood. Hello. To answer your question, yes, Chen En is here.
Wow.
Wow. Okay. All right. So, uh, these three, these three all contain something that is made from carbon and it's highly flammable. But if you have a piece of wood, not a flammable means can burn easily. Okay, so okay, so what happens here is if you have all these things, okay, all these things in big chunk. For example, if I only take a few pieces of wood and I just put them like that, like this, okay, will and I put a cigarette here and it falls to the wood. Okay, do you think it will burn very fast or very slow? Slow. It's not going to suddenly explode. It's going to burn very, very slowly. Because why does it want to burn fast? Okay, it's not going to burn fast. But then, if this wood is in a sawmill where it's cut into and there's all these little particles floating in the air, and some idiot doesn't even need to drop the cigarette, just decides to light the cigarette, stand there and light the cigarette. Do you know what's going to happen? The entire place will explode. Okay. Yes. Okay, so they ask in exam. So the reason I'm telling you this story is because they ask in the exam what causes the explosion? Because the surface area is really, really large. The surface area is really, really large. So things as simple as flour can cause an explosion. Teacher, flour can make bomb. No, it's not about the flour making bomb. It's because the flour or the sawmill or the coal dust is in tiny, tiny particles and they catch fire very easily because the surface area is big. It's super, super big. Can you understand? All right. So that's why, okay, what can I do? What can I do to prevent this kind of problems? How to get rid? In the factory, it's always flying one. How to get rid? Okay, get rid of stickers, yeah, but how do I get rid of sawdust? There is a way. How? Think. Smokers shouldn't be inside there at all, right? Okay, so that's not the point. But what if suddenly was a spark, maybe electricity short circuit or whatever? How can I prevent if there is a small spark? People won't die. It won't cause explosion. What can I do to make sure, like Caitlin said, make sure there's no dust in the air? How? How to make sure there's no dust in the air? What
Put
can
a
I
fan to
do?
blow them all to the ground.
Okay, close. A fan will not blow them to the ground. A fan will just keep them everywhere, right or not? Because it's so small particle. But it's a good idea.
Create a vacuum to
Not a
get
vacuum.
them
If
all.
vacuum, everybody inside there will die also lah. Something close, close. What can I do? Logic, logic. What can I do to make it sink? Water. How can I use water? I have water. There's tiny, tiny water sprinklers. Okay. All right. That's in certain areas. They actually have tiny, tiny water sprinklers to make sure it sediments to the bottom. But the best way is to make sure that nobody smokes lah. Make sure there's no spark or anything. Can understand? Huh? Increase the humidity. Something like that lah. Can. Okay. So do you remember the five factors? Concentration, pressure, surface area, catalyst. And I wrote for you the five ways, right? Okay, what are the five ways that increase the rate of reaction? When the temperature is, looks, yeah. Okay. When the concentration is high or the pressure is high, there are more particles per unit volume. So frequency of effective collision increases, the rate of reaction increases. Remember? Okay. If the temperature is high, the particles have more kinetic energy and more particles achieve activation energy. So again, they collide more often. The more often the particles collide, the more they react. Okay? When the particle size are smaller, the total surface area is larger, like powder. Powder will always be faster. And finally, I taught you about activation energy, right? Okay, so when I have a catalyst will lower the activation energy and it will make it easier for the reaction to happen. Okay, Ken? So these are the five factors. Okay, so last week I gave you the paper, this experiment, and this experiment. Did y'all do it? Did you watch the video? Okay. All right. So I sent this in the group chat also. Ah. It's right under the link. Yeah.
I just click the video one.
That's why maybe next time you should open your eyes bigger. Okay. Joe, do you do your homework? Silence. Joe, did you do your homework?
Uh,
Uh, okay.
uh,
Yes or no?
I don't know.
Okay. Anyway, let me just explain to you lah. Okay. So this is okay. Let's look at this question first. Okay. So this is one method we can use to measure rate of reaction. Okay, this is one method we can use to measure rate of reaction. Hydrogen peroxide decomposes to form oxygen. Manganese 4 oxide is a catalyst, okay, for this reaction. Two students investigated the speed of the reaction using the apparatus below. 2 grams of manganese 4 oxide powder was added. Please highlight the word 2 grams of manganese 4 oxide powder. Okay, to 50 centimeter cube of aqueous sodium hydrogen peroxide at 20 degrees Celsius. So this is a catalyst to make this reaction faster. This reaction is really, really slow. Okay, every 20 seconds they measure. Okay, now this is a gas syringe. I already told you gas syringe got reading, right? So what is the volume of gas collected here? 0. Okay. Okay, so please write 0.0. This one is 30.0. This one is 40, 45.0, 52.0, 56.0, and then 50, this 50, 54, right? And this is 60. That's 60. Okay, so obviously somebody is wrong. Who is wrong? This one is wrong, right? Okay, what do you call this kind of results? Anomalous. This is anomalous results, or it's called an anomaly. It's a result that doesn't follow the trend. Okay, it's called an anomalous result or an anomaly. It's a result that doesn't follow the trend. Okay, so using this, you are supposed to draw the graph. Okay, so have you guys drawn the graph yet? So it's going to draw the graph, huh? So yeah, they already do for you here. So it's actually quite easy. Huh?
Go back.
Yeah, sure. There. Okay, so let's draw the graph, okay? So 0 is 0. Okay, plot, please plot nicely. A cross or a dot, but usually we use a cross. Okay, so 0, and then at 20 it is 30. At 40 it is 45. At 60 it is 52. At 80 it is 56. And then this one is the wrong one. The wrong one we still plot. We still plot it. 54. And then what 54 and then 60, 60 or 50, 56, 54 and then 66. Okay, we still plot the graph, but you do not draw it on your graph curve. Okay, so you do like that. Okay, nicer than what I draw lah, because I'm drawing on the so ugly. Okay, you guys are drawing on paper and pencil, must draw prettier than me, ah. Okay, not bad. Okay, so the anomalous result, it's here. You do not join it in your graph. Okay, can? Do you understand? Okay, I give you some time. Okay, you draw first, okay? Yeah, do freehand. Okay, done? Try slowly, slowly, slowly. Done, ah? Okay, now, so last week we talked about this curve, right? Okay, so this is not part of the answer, but I want to refresh your memory. Okay, so in one reaction, if they ask you where is the rate of reaction highest, the rate is highest at the start. Here, rate is the highest. Why is the rate highest at the start? Because the concentration of hydrogen peroxide is the highest. Okay, and then how do you explain this part? So rate decreases with time. Remember? Okay, why am I telling you twice? Because obviously it's an important part in this chapter lah. Okay, rate decreases with time because concentration decreases with time. It's not part of your graph, but it's a very common question. Okay, concentration decreases with time. All right, concentration decreases with time. And then here, obviously, the rate is zero. If it doesn't increase, it's zero lah. Okay, so the rate is zero because the hydrogen peroxide is used up. Why can't I just say the reactant is used up? Because in a reaction where there's two reactants, you don't know which one is used up. You must say specifically, let's say the acid is in excess. Then you must say, oh, the magnesium is used up and so on. Get it? Okay. Okay? Do you want to answer? Do you understand? Okay. The rate decreases with time is concentration. Okay, which point in it seems to be inaccurate at 100 seconds? Why? It does not follow the trend. Hmm? Yes. No need to talk a lot. Just have to write the key points. The key points are the most important. Okay. Use your graph to find the volume that was produced after 12 seconds. Okay, please highlight or underline this part. Show clearly how you use the graph. Okay. Now, this kind of question. So at 12 seconds, so obviously 12 seconds here, right? Okay, you need to draw the line. No need to be dotted line. Why no need to be dotted line? Because you're not drawing this graph. Obviously, this graph can see. So at 12 seconds here, so you just draw a line like that. And then just draw like that. So you just need to show on the line how you show me your answer. So it's 21 centimeter cube. Can see. So one mark is from your drawing on your graph, and then the other mark is your actual answer. No need to explain, no need to explain. Why did the volume of oxygen level out at 100 seconds? Because hydrogen peroxide is used up. Okay? Hydrogen peroxide used up. So level out means flat. Okay, no more already lah. Can I understand? Okay. The experiment was repeated, but the hydrogen peroxide cooled down to 10 degrees Celsius. How could the hydrogen peroxide be cooled using a ice bath or a water bath at 10 degrees Celsius? Okay. Sketch on the graph. Sketch on the grid means you draw a graph that you expect at 10. So at 10 degrees Celsius, it's faster or slower? At 10 degrees Celsius, faster or slower if I pull it down to 10? Slower. But it will still be the same amount because I'm using the same volume. Okay? Same amount of reactants. So it's just, so the graph that you're going to draw, use pencil, don't do dotted line. Okay, like this. Okay, I want to show you. See? Like this. So just slower and then it finishes like that. Yeah, okay. It doesn't have to finish here as long as it shows that it will almost reach here but later on. Okay, got it? Okay, so this one will give you 2 marks. The graph, the gradient is less, is 1 mark. The volume is the same, is 1 mark. Get it? Okay.
For the last question stuff, you need to draw one line and you
Yeah, just a curve lah, a curve. It's a curve. It's just that I got so many things here, I cannot draw the curve. So the curve 它不是一个直线 it's a curve also. Okay. I draw for you. No, it's because I wrote so many things. Okay, let's pretend it's a curve lah. So like that. Lor. Yeah, it will eventually, but later on lah. So you don't need to draw this part, you just need to draw this part. As long as it's curve. Okay?
一定要一直去那个完。
And but end at the same amount. Total amount is the same. Okay, can? Okay, do you all understand?
Yeah.
Did you understand?
Yeah.
Okay. So this
Wait,
this
I
one,
just got home.
sorry.
I just got home.
Oh, okay. You can do this later. It's okay. Okay, this one you guys do as homework. Those who have not done it. Ahem. Okay, this one do as homework. Okay, what is the difference? What is that? You done already, so you got no homework. Okay, what is the difference? This one is using a measuring cylinder rather than a gas syringe. So when the gas is here, it will push down the water so you can still measure the volume. Okay, can? All right, so we're gonna continue with rates. This one we discussed already, right? This one? Did we do this?
Uh, I think
No, no, this part at the back here only, right? I haven't, right? We only done the first page, right?
Yeah.
Okay. We did the whole paper. Oh yeah, we did the whole paper already. No lah, we did the whole paper lah. Okay. You, yeah, we already got the answers here. Okay, so you guys have to catch up, okay? Huh? Have to catch up. Okay, so I want to share with you something. Okay, wait Now, this subtopic is called equilibrium. Okay? Now, what is a reversible reaction? A reversible reaction is when the symbol shows this kind of reaction. Now, for example, something that is non-reversible is like, okay, uh, carbon burn with oxygen, you get carbon dioxide. Okay, carbon burn with oxygen, you get carbon dioxide. Can the carbon dioxide change back to carbon? Can it quite
I
possible,
don't
right?
think that's possible.
I don't think it's possible, right? So it's a one way, right? Burn already cannot unburn lah. Okay, let's say fry an egg. The egg fry already can unfry or not? No. Okay, so you cannot undo a non-reversible reaction. It's just one direction. But a reversible reaction is like water,
oh,
liquid water. I freeze it into ice. Can I unfreeze it? Of course. So this is a reversible reaction. Okay, so a reversible reaction, you must use this kind of arrow. Okay. Now, we are going to talk about a few reversible reaction, and these are copper 2 chloride and cobalt 2 chloride. Okay, first of all, no need to copy everything. Can you all write down reversible reaction? Just write the words reversible reaction, and then this is the symbol, and then write this equation, this one. Okay? Don't need to write everything, right? Just write reversible, and then write the equation. So this one only, because this one is non-reversible. Okay, ready? Okay, your two best friends that you're going to learn today is called copper 2 sulfate and cobalt 2 chloride. Okay, copper 2 sulfate and cobalt 2 chloride. Okay, so let's start with copper 2 sulfate. Huh? Yes, copper is that. Yeah, Tom, right. Okay, copper 2 sulfate, the formula is CuSO4. Okay, now when there is no water in the crystals, this CuSO4 like this is called anhydrous. Anhydrous means no water. This is used to test the presence of water. Okay, how do I test the purity of water? Do you know that?
Electrolysis.
No,
yeah, yeah, fine.
presence of water. Okay, presence of water and purity of water is different. Purity of water means that sample that I have is 100% water, nothing else. Okay, presence of water is got water or no water. It can be longkang water, it can be water what you call that? As long as your water, it can be apple juice, can be anything, but it's got water or not. Purity of water is 100% pure water. How do I test for the purity of water? Every pure substance has a very distinct
Oh, boiling point.
boiling point and melting point. The boiling point of water is 100 degrees Celsius. The melting point of water, of pure water, is 0 degrees Celsius. This is how you test for purity, remember? Okay, presence of water, we don't use that. Presence of water, we use anhydrous copper 2 sulfate and also anhydrous cobalt 2 chloride. So anhydrous copper 2 sulfate is white color. It's a white color powder. When you add water, it will become something that is called hydrated copper 2 sulfate. Hydrated copper 2 sulfate is CuS4 dot 5H2O. Okay, why 5? Can I change the number? No, cannot. It's 5, meaning that the copper sulfate compound has 5 water molecules joined together chemically as a crystal. So this is a white powder and this is a blue crystal. So if it changes to become blue, it is water. If it doesn't become blue, if I put alcohol inside, it won't change blue lah. Okay, if I take this blue color crystal and I heat it up, will it change back? Yes, it will change back. So this one is reversible. Okay, so can you write down purity of water is how to test purity? Presence of water, you use this method. Can you write this down, please?
Like, how many you can shoot it,
If you heat it up, it will change back. Okay, so when I have anhydrous copper 2 sulfate, it's white. Okay, when I have anhydrous copper 2 sulfate, it's white. Okay, so here is anhydrous. When I add water, it will turn to become blue. And if the blue one is called hydrated, if I heat it up, it will become white again. Do you understand? Okay, now what does the few things that you need to understand? Okay, what does the 5H2O mean? What is it known as? This is known as the water of crystallization. It's not just random number. Okay, it's called water of crystallization. You need to know the name. Okay, so it's called water of crystallization. What does it mean to be hydrated? What does the word hydrated mean? It means there are water molecules chemically bonded. Okay, they are water molecules chemically bonded. Okay, please write that down. The word hydrated is called, meaning is water molecules chemically bonded, and water of crystallization is this thing here. Okay, so when you see the blue crystals, is this one. When you see the white powder, is this one. Okay, then, all right, the other thing that can use to test for the presence of water is cobalt 2 chloride. Same thing. Anhydrous cobalt 2 chloride, but the color is different lah. Okay, anhydrous cobalt 2 chloride is, now it's the other way around, it's blue. When you add water, it becomes hydrated. Okay, this is pink, this is blue. Okay, please write this down. Can see it or not? Okay, ready? All right. So now, what does it mean to have a reversible, okay, reaction? Okay, so first of all, let's say we are all working we are all working in making sandwiches. Okay, we take bread, take egg, and make a sandwich. Okay, I first start with 200 bread, okay, 100 egg, and I'm making sandwiches. Okay, so at first when I start the reaction, how many sandwiches do I have? Before zero lah. Haven't make mah. Okay, and then after that I make already. This one will become lesser and lesser and lesser, right? And then this one will become more and more and more, right? Okay, now in the end, eventually I will finish off all of this and I will have all sandwiches. Okay, now a reversible reaction, this is a normal reaction. Okay, a reversible reaction is not like that. A reversible reaction is at first like this. Okay, and then after a while, 180, 90, 10. Okay, what will happen is this sandwich, somebody standing here taking the sandwich and split open again to change back to bread and egg. Huh? That means the same time somebody is making the sandwiches, someone is unmaking the sandwiches to change. Huh? So at first, of course, I will still have more sandwiches because people are doing this faster, got more of this to do. So what happens is another person is changing it back. Okay, so another person is, so will the reaction ever stop? No, it just goes round and round and round. So someone make the sandwich, make the sandwich, make the sandwich, then suddenly someone unmake, then you have to make again, then someone unmake. It goes round and round and round and round and round. Okay, but at a certain point, maybe at the start, because at the start, I have a lot of the ingredients. I have a lot of the reactants. So maybe at the start, this one 90%, this one 10%, right now. And then as I make more and more and more and more, maybe over here, this one 70%, this one 30%. And then suddenly as I'm making, suddenly this one become more. This one becomes 70% and 30%. But then as I continue, then it suddenly becomes
30%, 70%.
okay, 70 and 30 again. Okay, and then after that, after 1 hour, it's still 70%, 30%. Did it mean that the reaction stopped? No. It means that how fast people are making and how fast people are unmaking has become the same speed. There's no overall change anymore. There's still a reaction going on, but this one is the same speed. When they reach a place where they are happy, this is called equilibrium. Okay, so a system, a closed system. Okay, I want you to write this down. A closed system Okay, I want you to write from here. A closed system is at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. Going forward, going like this, making the sandwich is called forward reaction. Unmaking the sandwich is called reverse reaction. So the rates of the forward and the reverse reaction is equal. And then the concentration of the reactants and product no longer changing. It doesn't have to be the same. It's not the same. It's just no more changing. 70%, 30% means 70%, 30%. It doesn't change anymore. Okay? Okay. Done? Okay. Now, ready? Ready?
Yeah.
Okay. Hydrogen and iodine becomes hydrogen iodide. Hydrogen iodide break apart to become hydrogen iodide. Okay? This is called a reversible reaction. If mm, this reaction, right? Now, this is at 30%, at 70% is at 30%. Okay? So, the percentage of a product is called the yield. Okay? Okay? The percentage of the product is called the yield. Now, do I want to make it go more product or less product? Of course, I want to make it go more product, right? Okay? So I want to increase the yield. Okay? Now, increase the yield means I want to push it to the forward reaction or the reverse reaction. Forward. So, I can change the conditions to make it go this way. Changing the conditions to make it go this way is called favor the forward reaction, or it's called shifting to the, this direction is the right. Okay? So when I do something and I ask you, will it increase the yield or decrease the yield? Then you must tell me increase the yield. Why? Because doing this thing will favor the forward reaction. Okay? Now, if a reaction goes this way, it will decrease the yield. So going this way is called the reverse reaction. And then it's called shifting to the left. Lah. Make sense? Okay. Now, in a normal scenario, we want it to shift to the right, shift to the left. Right. Okay. Some people during exam, they do until left and right also they don't know. Okay. So, you don't have to say shift to left, shift to right. You can just say forward and reverse. Get it? Okay. What are the 5 factors that affect rate? So this is yield. Increasing it is called yield. So now we're going to talk about yield versus rate. Yes, yield is percentage of the product. Rate is how fast. Okay? And okay, what is the factor that affects rate? Temperature. There are 5 factors. This one I taught you. Temperature. Some more? Okay, surface area. Some more? Catalyst. Some more? Pressure. Pressure. Concentration. Surface area. And catalyst. Okay? Correct? Are these the 5 factors? Yes, sir. When the temperature is high, the rate is high. Yeah lah, I have big fire and small fire. Which one cook faster? Big fire lah. Alright? When the pressure is high, the rate is high. When the concentration is high, the rate is high. When the surface area is big, the rate is high. When the catalyst is present, the rate is high. So easy, right? Rate so easy, right? What about yield? Yield depends. If I put the yield, if I put catalyst, this one before I put catalyst, it's 30%. After I put catalyst, how many percent? No change. No, it doesn't change. Catalyst doesn't change. Catalyst only makes it go faster. It doesn't change the percentage. So this one, no change. Does not affect. No effect. Surface area, also no effect. Temperature depends. Depends. If I write like this, this is an endo-exothermic reaction. Negative is what? Negative is exo. Negative is exo. So that means go this way, absorb heat, release heat. No, absorb or release. Exo is release, endo is absorb. Negative is exothermic, right? So going this way, it will release heat. Understand? Exo is release heat. If I write positive 50, endothermic. Going this way, it will absorb heat. Okay? If this way is endo, this way will become exo. If this way is exo, this way will become endo. Get it? Depends on. Okay? So, if I put high temperature, the endo very happy. But if I put high temperature, the exo very sad. Exo very hot already. You don't like high temperature. But endo loves high temperature. So in this reaction, I make it high temperature, it will go forward or go backward. Now if I tell you it's exo, I tell you it's endo. I tell you it's this.
Okay.
So if I put high temperature, it will go forward or backward? Forward. If I put low temperature, it will go backward. But if this is exo, and I put high temperature, then it will go backward. Understand? So how to explain? So temperature, high temperature favors endothermic reaction. Okay, so it's not high temperature, high yield. It depends. If the forward is endo, then good lah. Okay, now pressure. All of these are gas, all of this is gas. How many gas do you see here? This is the one I circle. How many moles of gas do you see here? One. How many do you see here? Three. So total here, how many? Four. Okay, how many do you see here?
Four.
Two. Two of this, ma. Two. Get it or not? How many is the number in front? Okay.
I thought that.
That is atom. I'm asking you molecule, mole. Okay. This one 4, this one 2. Okay. Who has less moles of gas here? Okay. If I put high pressure, I'm squashing them together or giving them space. Squashing. So if I'm high pressure, I'm squashing them. They want less people or they want more people? Less people. So high pressure favors less moles. Okay? Okay? High pressure, it will go. If I put high pressure, it will go this way. Because it's only 2 here, but 4 here. No space. High pressure means I'm squeezing it. Okay? Now for this reaction, if I put high pressure, what happens? This reaction, if I do high pressure, what happens? Nothing. No change. Why? Here 2, here 2. Get it or not? Okay? So, again depends. High pressure favors side with less moles of gas. Get it? Okay, last one, concentration. Okay, this is the easiest one. Okay, if I add, a lot of this, I add a lot of hydrogen. What will they try and do? Make more hydrogen or take out the hydrogen? So if I add a lot of hydrogen, it will go this way. Get it? Then my yield will be higher. If I remove the hydrogen, I take away the hydrogen, then what will happen? Which way will it go? It will go this way. Understand? So if I add a lot of hydrogen and a lot of iodine, which way will the equilibrium go, forward or backward? Forward. They want to remove it, yes. So high concentration of reactant favors product. Make sense? Okay. Please write this down. Do you want to copy here? Or no need? Or just here?
15.
Just here. That one you can just, I will send you this, but I want you to have this in your notes. Okay, yeah? Okay, so okay. Okay. I'm gonna teach you something called we're gonna try. Okay, this one next week I'll do, okay? Next week I will do the rest. Haber and contact and everything. These are different processes. I'll do this next week. Okay? So this week we have done this already. Okay, I'm gonna give you some scenarios and then you tell me what happens when you change the temperature and the pressure, okay? All right? Okay. So, so this is a reversible reaction, okay? Okay, can you write down this question? It doesn't stop. It reaches equilibrium by itself. It's happy already. That means the rate of the forward and the reverse are equal. So that's the definition of equilibrium. Okay? Why would they? It's not they pick a reaction, it's the reaction happens to not stop. No, it will just keep going forward, backward, forward, backward. Ah. It only reaches a stable equilibrium, that means in a certain percentage when it's in a closed system. When you open it to the air, it changes, but it diffuses everywhere. Ah. If you don't know the first one, it's okay. Do the rest. Not vanilla. Okay, four only. The first one you don't know is okay. So what is a closed system? Now, when I want it to reach equilibrium, what I do actually is I put it in a container that is a closed system. And then I close it completely because first I put hydrogen and iodine. Then the hydrogen iodine will react to form hydrogen iodide. And then the hydrogen iodide will react, split apart to become hydrogen iodine again. And then it ding dong, ding dong, ding dong, ding dong, and then reach equilibrium. The reaction is still happening, but it's at the same percentage. Okay, it has to be a closed system. If not, the hydrogen can just diffuse out, or more things can just diffuse in. Okay, so a closed system means the reactants and products cannot escape or be added. Okay, okay, what happens to the yield if the temperature is increased? Increase or decrease the yield? Decrease. Why? Because, okay, so how you write is because high temperature favors the reverse reaction, which is endothermic. Okay? So if this one, exo is negative 51, then if I say what is the reaction in the endo, the reverse reaction, what's the energy, is positive 51 kilojoules. You cannot just say 51, it must be positive. So if this direction is negative, this direction must be positive. Get it? Okay. What happens to the yield if the pressure is increased? No change. Why no change? The amount of moles of gas in the reactant and products are the same. In front also 2 moles, behind also 2 moles, so it's the same. So no change. Can you understand? Okay, last question. What happens to the yield if hydrogen is removed? If I remove hydrogen, then it will shift where? Forward or backward? Backward. Okay, so the yield decreases. Because the reaction shifts to the left to produce more hydrogen. So you take away the hydrogen, I try and make hydrogen now. So actually this chapter very easy, right? It's actually very easy, right? Okay.